Right. Then we look at the general plane motion, the figures of the concept motion is shown in on your right hand side. So we have a rigid body that is translate. At the same time, there is a rotation, just like a wheel, right? And then so there is a concept here that we should understand. The first one will be the mass center. So the mass center uh, can be calculated, can be determined, and sometimes defined for you. Um, and the body will rotate with the same angular velocity omega. Um, yes, and then we can define the kinetic energy of the whole body is equal to the kinetic uh, energy for the whole mass, half mv equals to 2, plus half moment of inertia about the mass center, right? Moment of inertia of body about the mass center. So the interpretation is also given. It tells you that the kinetic energy actually has a component. The first one is the total kinetic energy consists of the kinetic energy due to the translation, and the other component is the kinetic energy due to rotational motion of the body. And then there are various ways that you can use. They give you the same meaning, right? Um, the kinetic energy of the plane motions can be also explained in terms of rotational velocity about instantaneous center of zero velocity. So the concept of instantaneous center of zero velocity also mentioned in when we consider the same day that I give you the quiz that describe um, um, the angular body inside angular motion. You have to show that they having the same angular speed, and the note describing to you about the variation of velocity for the wheel as it move on the ground. So at the contact surfaces between the wheel and the surface, that will refer to instantaneous center of zero velocity. So we can say that the kinetic energy can then be given by half, and then the moment of inertia about the center, instantaneous center of zero velocity time the um, rotational speed of the body power of 2. So this moment of inertia about a point of rotation needs some clarification. So there are various type of body that you can find in Appendix B. Right. So before we go to the uh, uh, details about the moment of inertia, it's very important for us to look at the fundamental of this moment of inertia. So we have a rigid body. Uh, we have this body having a fixed rotation, right? One type of motion for rigid body. If you look at the figures, uh, the plane at which this body is rotating is no longer uh, normal to the screen that you look at, but it's rotate now in towards the screen, right? So the axis rotation is upward, right, using the right hand rules. right hand rules. Oh yes, no. Well, you have that rotation because you have a force acting on that the MS, um, and because of that force, the system is rotating in the um, anti-clockwise direction, right? So when the body rotate about axis, right? A point, for example, OO, and the body has angular acceleration because of this net force, right? So all the particles of the body will move in parallel plane. So the parallel plane, sometimes you call it vertical plane, or right? And this plane is normal to the rotation axis, right? So you have vertical plane, and then you see the body is rotating over the plane, right? So this is what it says. The plane is normal to the rotational axis. In the exercise, normally you don't see the axis, it's just a pin, right? So you don't see it, you just see the motion. So if you look at a very small mass that has, when we look at the anti-coordinate system or in spherical polar coordinate system, if it has uh, angular acceleration r alpha, right? R is the radius, alpha is the angular acceleration. So the body will receive tangential force, right? So we can accept this one because you look at the kinematics of the particles, right? So you have R alpha. Um, the other components that when the body is, we have the plus 2 times R dot, right? First relative, and then we have theta dot, right? But since the rigid body, the body does not move inside the body, right? The element does not move inside the body, so it's a rigid body, right? And there is no deformation. So the only force acting on the element is just R alpha, right? And then when you have a force that act at the radius of location, it create a moment. So you have a moment of force, R alpha dm, right? And time the distance. So we have R equals to 2 alpha dm. So when we look at the summation of moment of all forces acting on the body, right, element of body, we have to include the integration. So the moment of inertia actually the integration of the all element inside the system, right? The element in the system times the radial location, right? And then does not include its angular acceleration. So the mass of moment of inertia is a resistance to rotational acceleration. That is an interpretation of the moment of inertia, just like a mass, right? The bigger the mass is very difficult to move, to translate, right? If it is translation, it's very difficult. You need a very large force to make it stop. Similarly, the system with a high moment of inertia, if it is rotating, you need a very high moment force to make it stop, to decelerate it. And it is a very large, you need more force or more moment to make it move, right? Now, normally we look at the cases when the system are moving in XY plane, right? So we have a plate here, a thin plate. So the moment of inertia of the plate uh, uh, about the z-axis through O is designed as delta O, right? If O is the mass center, so it will be IG. Now, there are concepts that associate with the moment of inertia, right? You can find this concept in various exercise. This concept called radius of gyrations, right? So when we look at the definition of inertia, we have integration of uh, distance power of 2 times dm, right? The mass of element inside the rigid body. So radius gyration is defined by the square root of moment of inertia for the body, um, and we have to know location of the axis of rotation, right? Divided by the mass of the rigid body, right? So normally the value of k is given to you, right? And from that we can calculate the moment of inertia of the body about an axis of rotation, and this equation is given in appendix B slash 2. Here is the typical geometry that normally you will use in solving problems in kinetics of rigid body, right? We have a slender rod. So slender rod is very small radius body, right? It's long, and this equation that I mentioned here, um, it tells you about the axis of rotation given by, for example, the uniform cylinder rod. So the moment of inertia about the axis y, right? So 1 by 12 times mass times the length of the rods, right? So if you, let's say this rod is rotate about the mass center G, right? So it's I, moment inertia about axis y, right? Now, if we look at the second for uniform cylinder rod, the moment of inertia about the axis of rotation y1 and y1, right? So 1/3 times the mass of the body times the length power of 2, right? And next we look at the circular cylinder. This is a solid cylinder with a circular cross section. The length is L and the radius is R, right? So we want to know the moment of inertia about the axis of rotation XX, which is uh, axis through the mass center when observed uh, normal to the axis XS, axis rotation. So we have quarter mass times the radius power of 2 plus 1/12 mass length of the rod cylinder power of 2. But if you look at the disc, this is a very thin circular cylinder, right? And the axis of rotation is through the mass center, and about the z axis of rotation. So it will be half times the mass times the radius of the disc power of 2. And then we have sphere. So sphere, moment of inertia through the mass center, and about the axis of rotation is coincide with the mass centers, right? The line of axis of rotation. So the moment of inertia is given by 2 by 5 times the mass times the radius of this solid sphere. So we'll consider the examples in a book, because the example in the books help us to understand more about what is the moment of inertia, and then what is the translation